So, hello everyone. Today we'll start our second class. Okay, so uh, uh, so so in previous class, what we have discussed is about ideal gas law. So initially started from ideal gas law by stating some empirical laws like how the pressure is dependent onto the pressure is dependent onto the volume, or volume is dependent on the temperature, and pressure is dependent on the temperature. So we started from these laws, empirical laws, and we from that itself we have developed the ideal gas equation, that is PV equal to nRT, or you can write it like PV equal to this is capital N, sorry, or PV equal to PV equal to NKT, or PV equal to nRT. Okay, where the mole, this N is basically the number of moles, that is basically N by Na, and R, that is the ideal gas constant, is related to Na by Kb. Kb is the Boltzmann constant, Na is the Avogadro number. Okay, and from there itself we have described the basic postulates of kinetic theory, right? Kinetic theory. From the kinetic theory itself, we have developed uh, using this law of kinetic theory, we basically develop the distribution or the fraction of gas that has speed between C to C plus dc, right? We have developed the distribution, gas distribution basically, or molecule distribution, whatever, distribution between C to C plus delta C, where C is basically the speed of the gas in 3D. Okay, and that distribution is basically dnc equal to 4 pi n. Dnc is basically fraction of gas molecule that having this amount of speed, is basically given by this, right? 2 pi kbt by 3 by 2 into e to the power minus mc square by 2 kbt c square dc. Okay, and the distribution is basically dependent on the like temperature, mass and all. So if you plot the distribution for different temperature, it will looks like this basically. That means if you increase, so these are the temperature T1, T2 and T3. Okay, where T3 is the highest temperature, so T3 is greater than T2 greater than T1. So basically if you increase the temperature C by this is C. Okay, so basically that means if you increase the temperature, the mean of the distribution will be shifted to this side, the higher value, basically higher value of speed. Now if you, from this distribution we have calculated many things, like one is mean speed, that is 8 pi kbt by m. We have calculated the RMS speed, what that is given by this uh, under 3 kbt by m, and we have calculated the mean speed also, that is most probable speed, sorry, this is the mean speed, this is the RMS speed, and this is the most probable speed. Okay. After that we have also discussed about how, like what is the degrees of freedom of a molecule, like let's suppose for a monoatomic molecule in 2D and 3D, or of a rigid diatomic molecule, or if it's instead of a rigid, if it has a spring connected between them, if it has a additional vibrational degrees of freedom, in that case what would be the total degrees of freedom for the system? For a diatomic, triatomic case you have calculated, and from that degrees of freedom, how can you basically calculate the internal energy from of the system? That is basically given by this formula, equal to F by 2 n kBT, where F is the number of degrees of freedom, and from that itself you can easily calculate different types of specific heat like Cv, that is del U by del T at constant V, or Cp, that is del U by del T at constant P. And Cp and Cv basically related by this relation, which is a very useful relation, Cp minus Cv equal to R. And you can also calculate the adiabatic exponent, that is gamma equal to Cp by Cv. Okay. So if you know the degrees of freedom of the molecule, you can calculate basically all of these quantities. Okay. So these are the things that we have basically discussed in the previous class. Okay. Okay. So now, in today's class, we'll initially start from what is this called? Okay. Gas collision theory, mean free path, mean collision frequency, and all. And after that, we will also solve some problems also. Okay. So as we know that uh, when gas molecule moves, it doesn't follow a straight way, right? So there are like let's suppose this is a tagged gas molecule. So when it moves in the atmosphere, there are also other gas molecules are there, right? So it will collide with those molecules and it will follow this kind of a zigzag kind of a way. Okay, so it doesn't follow a straight linear way. Okay, so it basically collides. Okay, so this collision basically has a frequency. So as it suffered collision, so that's because of that its mean free path is also changes. Okay, so we will calculate we will show how to calculate all of these things. So let's suppose this is a tagged molecule. So during the movement, let's suppose it initially move x1 amount of displacement, then after the collision it moves x2 displacement, then after x3, so like this x4. So for this particular molecule, this mean free path will be looks like this. Okay, mean free path or average path, whatever it is. So the expression will be looks like this, just the mean of all the distances before each collision, like in between each collision. You have to sum up all those distances divided by the number of collision. Okay, this gives you the mean free path. Okay, uh, this gives you the average path. Sorry, this gives you the average path. Now now if you calculate this, so this also be calculated using this also. Okay, so if you know the tau, that is the time between each collision. If you know the tau, that is the time between each collision, and the average speed, that is the c bar of of this particular molecule, then from that also you can calculate the average part of the mean free path. So that in that case it would be related by this x bar equal to c bar into tau. Okay, where tau is basically what is this called, uh, time between, average time, you can say average time between each collision. Okay. So now, so this is for a single molecule you can calculate. But if suppose there are in a gas assembly there are many molecules are there, right? So n numbers of molecules are there. So for calculating like individually for each of the molecule is not possible. Okay. So for that we have to use some statistical approach. So we assume that, let's suppose dn1 number of molecules are having mean free path between x1 to x1 plus dx1. Okay. dn2 number of molecules are having free path, let's take x2 to x2 plus dx2. Okay. So like this, if there are like, let's suppose total number of molecules is n, and n is basically summation of all these things d. Let's take dn, n equal to summation of dn1 plus dn2 dot dnn. So each of the fraction of this molecule are having like mean free path from x1 to dx1 or x2 to x2 plus dx2 like this. In that case, the mean free path of the entire gas assembly, the similar way we can calculate here also. So x1 into dn1 plus x2 into dn2 plus xn into dnn like this. Similarly, the whole thing divided by dn1, dn2, dnn like this. To calculate this, now this whole summation you can write this whole summation in the form of an integration, right? So in that case it would be total number of gas molecule, let's suppose is n, so it would be n into x into dn. Okay. And the integration limit would be this whole length. Okay, because if let's suppose the gas container has a length of L. Okay, so this range of this mean free path can vary from 0 to all the way to the maximum limit of the container, right? That is the length of the container. So that's why the integration limit would be from 0 to L. Okay. Similarly, so lambda is basically mean free path. Similarly, for you can also calculate the frequency of collision, right? The tau thing. Okay. So the tau thing also you can similarly calculate. It's like the same way. Like if suppose uh, a number of like DNA1 number of molecule are having mean free path between mean free collision, like collision time as t1 or tau1 to tau1 into plus delta tau1. Similar dn2 has tau2 to tau2 plus delta tau, like this. So in that case, the tau would be uh, tau can be written as 1 by n0 into integration t into dn. Okay, so let's, instead of tau, let's take it as t1 plus t1 to t1 plus dt1 t2 to t2 dt2. Okay, so now the here the integration limit would be so here the tau is starting from 0 to the maximum value of tau that it can attain is number of length, the total length of the box divided by the average speed. Okay, that is the maximum time the gas molecule can get before a collision, between two collision. Okay, so it would be L by C part. Okay. Now, since this frequency, this average distance between each collision or average time between each collision is very high compared to very low compared to L. So lambda, the number, if you see the lambda, that is the mean free path, is very less compared to the L. So we can write this integration as 0 to infinite. Okay, x into dn. Or here also the tau is basically very small compared to L by C bar. So you can write this integration also 1 by n0 to 0 to infinite. Okay, since the L by C bar value is very high. So into uh, t by d. So this way, so this is basically the expression of, in terms of the integral expression of the mean free path, that is this, and the average collision time. Okay, that is this tau or t into d. You can write this thing as infinite because its limits are very high actually. So anyway, okay. So now, so this thing is dependent upon the x and this thing is dependent upon the time. So our next so next thing is that to derive this thing, what you have to do, like you have to basically express this thing in a closed equation, not an integral equation. Okay. So for that, what we can do, we have to find out this expression of dnx and dnt. Okay. So for that, what they have used that. So let's take initially n naught number of gas is there. So okay, n naught number is gas out there. So after traveling a certain distance x at a time t, okay, let's take so from this gas assembly, certain number of molecule will be kicked out from this gas assembly due to collision and all. So the reduced number of gas molecules that we have, let's suppose it's n. Okay, this is a reduced number, so n. So n is basically uh, related to n naught by this relation, n equal to n naught into fx. Okay, so fx is basically is the probability that a molecule travels x distance without suffering collision. Okay. So that means if you basically, yeah, that means basically if you multiply the total number of, so n is basically the number of molecules that doesn't suffer the collision between this x distance, right? So that means if you multiply this n naught to the probability that the molecule doesn't suffer any collision, that basically gives you the number of molecule that will survive in between this distance x, right? Okay. So our main goal would be to calculate this distance x, this function fx. Okay, so how this function looks like. Okay. So this function we can write in terms of, if you have any question you can ask.
Yes, so my question is that the total number of molecules should remain the same, right? Because even after collision, the molecules are not disappearing. So why are the number of molecules decreasing? Like,
So what happens, like in the gas assembly, let's suppose this is the total gas assembly. Okay. So we are considering a certain number of gas molecule. Okay, n naught, not the whole gas assembly. Okay. So from
yes.
that gas assembly, a certain number of molecule we are only taking into our account. So that now that gas molecules, if it moves a certain distance x, okay, So from that assembly, some gas molecule will be kicked out from that assembly, right, due to collision, right? So now the remaining number,
So due to collision,
let's
no, so
take,
due to the collision, the particles will be there, na? So the
huh,
total number of
in the
molecules is the
whole
same.
system, the particles is there in the, like, the total in, if you are in a chamber, okay, but from that, let's take,
Mhm.
you took a particular volume, let's take dv, na dv volume, okay. Inside the dv volume, let's take n naught number of gas molecule is there. If that volume moves in the space, so it will, so inside the dv volume, whatever the molecules are, they will suffer collision. So because of that, the some molecule will be comes out from that volumes, okay. So we are only interested the molecule inside that volume, okay.
Oh, okay,
Yeah,
okay,
not the entire gas container, okay. Inside the gas container, the total number of molecule will be fixed, that you are correct, whatever you are saying, okay. But we are also
okay, got it.
considering the specific, like the particular amount of volume, okay. Like dv in this, let's say this is a small volume element dv, okay. So so that's why we are multiplying the total number of molecule with the probability fx, that it doesn't suffer a collision, okay. So so we want to find what is the expression of fx, okay. So so okay, yeah. So we can write fx plus dx equal to fx plus, so before that, let's define px dx. So px dx is basically probability of a molecule suffer a collision in x to x plus dx, okay. So px dx is opposite to f dx, okay. So it's basically gives a probability of a molecule that suffers collision between x plus dx. Previously it was just in x distance, okay, for case of fx. So so we can write fx dx is basically, that means the probability of molecule that doesn't suffer a collision between x plus dx. So that would be the multiplication of fx into 1 minus px into dx, okay. So this is basically what you can, the joint probability, okay. So what you can, so you can then basically write this thing. You can basically expand this function to the first order approximation like this, del x dx, just like you do in Taylor series, okay, up to first order Taylor series expansion. And here also you can write it like this, fx minus fx px dx. And by comparing the coefficient of dx, you can write dfx dx into minus px fx, okay. Now from it you can write the expression of fx as, if you solve this differential equation, it will just gives you fx equal to a into e to the power minus pxx. Now from the so now from the initial condition, if x is 0, so initially no molecule will suffer any collision. So f0 is basically 1 at x equal to 0. So it gives basically this probability, if you plug it in here, it basically gives this constant a, this integration constant value a equal to 1. So in that case, the fx should be gives you e to the power minus pxx, okay. Okay, now from here you got the x, so from there you can calculate the nx equal to fx into n0. So it gives you n0 into to the power minus pxx. Now from here, if you do the integration, like if you do the differentiation both side, if it will gives you dn equal to minus n0 px e to the power minus pxx into dx. So we got, so we need basically the dnx thing that we have calculated already here, dnx. So this is a function of x. So you got the expression of basically dnx. Now Just substitute. Let me just give some equation names. So this, let's call equation 1, and this call equation 2, and let's call it as equation 3. Now if you now sorry. So now if you put equation 3 in equation 1, you will get uh, lambda equal to 1 by n 0 to infinite n0 to dx x e to the power minus px x dx. And if you do simply the integration, it will gives you 1 by px 0 to infinite px into x e to the power minus px into x dx. Do the integration, it will give you 1 by px. Okay, so that means the that means the lambda, that is the what is this called, this mean free path is nothing but one inverse of the probability of the collision between distance x to x plus dx. Okay, this is a very important relation we got here. So now what we can do, we can basically from here we can calculate the survivability equation. What is this called? So fx is basically, we can write as we know fx expression, right? So these expressions are very important. This px into x, right? So px we know is 1 by lambda, so it would become e to the power 1 by lambda x. Okay, now from here you can write nx equal to, so we know this relation, right? This thing. So sorry, this relation, right? So from this relation you can write the n equal to n0 to the power x by lambda. So this equation is called, what is this called, the survival equation. Okay, so this is a very important equation. You have to remember this equation. Many, like in exam, many problems, in order to solve many problems, you have to basically use this equation. Okay, so let's suppose there is n naught numbers of gas molecules is there in a container. Okay, so after traveling a distance, particular distance x, if you want to calculate what is the number of gas molecules there, n naught to n. So in that case, the n is related to the n naught using this relation. Okay, x by lambda. Lambda is the mean free path. Okay. Similar way, uh, you can also calculate the tau also. Okay, the collision time, the mean collision time. Okay, so uh, so at a particular, let's suppose instead of x, let's suppose at a particular time t, so t equal to 0, let's suppose a particular gas assembly is there. Okay, so after a certain time interval, after a certain time elapsed, let's suppose t is the time after which you want to calculate how much number of gas survives. Okay, so in that case nt would be similar way. Okay, uh, n0 into e to the power t by tau. Okay, this is like in terms of space, this is in terms of time. Okay, so these two are basically very important equation. You need to remember these two equations. So this is the lambda is the mean free path, and tau is what you can do, like you can say it's like a collision, average collision time. Okay, something like that, average collision time, like between each two collision, what is the average time between two successive collision. Okay, so So these actually in a gas you can basically using some experimental method you can basically calculate these quantities, this lambda, tau, and all of these quantities basically can be calculated. There are certain experimental instruments are there. Using that those instrument you can basically calculate this lambda, tau, and if you can calculate this lambda, tau experimentally, after that you can basically calculate what is the expression of nt or nx. Okay. 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 Yeah. So now, yes. So there is also a relation of if you know the diameter of the gas, or what is this called, average cross section, if it's a gas molecule is moving like this, so in that case the diameter sigma, that gives you, so if you calculate the sigma of this gas molecule, okay, so basically in between this particular range sigma, if if any other gas molecules comes, then it will suffer collision with that gas molecule, right? So the sigma basically gives is the kind of effective radius of this particular gas molecule. So this tau is also, sorry, not radius, it's the effective diameter. Okay. So this tau, this collision time basically also related to this sigma also. So the relation is basically given by this tau equal to n c by sigma, where n is basically the density, not density, it's called number density. Okay. It's different from normal density. So number density, that is the number of gas, total number of gas in the container divided by the volume. C is the speed of the molecule. Okay. So this is a very important relation. Tau is like 1 by nc sigma. And similarly, if you know tau, you can calculate lambda also. Right? Lambda is related to the tau using this relation c bar into the tau. Right. So lambda is basically c bar by n sigma c. Okay. Now there are multiple. So and sigma is the cross section area. Yes. Okay. Now there are there are basically multiple ways to calculate this. What is this called? Yeah. So there are basically multiple ways of calculating this sigma. This is effective cross section, and also this C. Okay. So for a particular for a spherical kind of a monoatomic molecule, okay, if it moves in space, in general, so first is the sigma. What is the expression of sigma? Expression of sigma. Okay. So in general, what happens if this is a molecule? Let's suppose it has a uh, radius of d. So when it moves, okay, when it moves, so only as we have previously discussed, only if the molecules comes in front of this area, that is its cross section area, that is by, given by a equal to pi d square. If any molecule comes inside this cross section area, then only it suffer the collision, right? So the sigma expression is basically given by pi d square in general for a spherical molecule. Okay. And for C, expression of C, there are like, so there are like many order corrections are there. So there are like zeroth order correction is there. So zeroth order correction. So according to the zeroth order correction, so zeroth order correction basically assumes that all the molecules are basically frozen. Okay. So the only the tagged molecule that having the velocity c, that is only moving. Okay. So moving with mean speed c bar, and all molecules are basically frozen. So in that case, c is basically equal to the mean speed of the gas, that is c bar. That is one of the way, the very rudimentary way to calculating the c. Next is you can also use the first order correction, that is basically uh, postulated by Clausius. Okay. So here what Clausius had postulated is that all molecules, so here apart from the tagged molecule, every molecules are frozen in the zeroth order case. In the first order case, what he have stated is that all molecules traveled with c bar but in different direction, and velocities are also different. Okay, so here all molecules travels with c bar but different directions. Okay. So this was the first order correction. So here like all the molecules, like every molecules, this is, let's suppose, is the tagged molecule, and all other, apart from the tagged molecule, all other molecules are all moving in different direction with c bar, mean speed c bar. And this is the tagged molecule. By considering this thing, so he has applied all this the concept of this relative velocity. So let's suppose the tagged molecule, like these are the molecules, right? So these are c bars, all molecules are moving with different speeds c bar, right? So in that case, the, let's suppose this is one molecule is moving in this direction with velocity c bar, another molecule is moving this direction with same velocity c bar, and the angle between them is, let's suppose, theta. And if c is the, what is this called, resultant velocity, so in that case cr, let's suppose, so cr would be basically, we know, c bar square plus c bar square minus 2 c bar into c bar cos theta, right? So this gives you cr equal to 2 into, sorry, 2 inside 2 c bar square minus 2 c bar square cos theta. So now if you consider, like, let's suppose particular area dA, the expression of the area, let's suppose r square sine theta d theta d phi, with having a solid angle d omega. Okay. So inside the solid angle, if you calculate, so inside this small area dA, if you calculate the average number of, like, average expression of the velocity, so it basically gives you, if you do the integration and all, the cr bar basically gives you a kind of an integration like this: 4 pi 0 to 2 pi d phi into 2 c bar sine theta by 2 sine theta d theta 0 to pi. If you do this, all of this integration, you will get CR bar equal to 4 by third into C bar. Okay. Now, if you put it into the expression of lambda, this gives you basically, so lambda expression you know is basically this C bar by C. So C bar by N sigma by C. So C bar C is so just plug this CR bar here into the expression of C. This gives you lambda equal to C by 4 N sigma. Okay, that is kind of 0.75 N sigma. So this is after the first order correction. Okay. So in the first order correction, the important thing is first order correction. So the zeroth order correction is like every like the tag molecule is moving with C bar. That's it. Okay. Every other molecule is frozen. And the first order correction is like every molecule is moving with a particular velocity c bar but in different direction. Okay, so from that we calculate like it's this calculation is basically done in every book. Okay, you can check this whole calculation. Okay, so like every molecule is like having with a particular velocity c bar in different direction. From there you can calculate the resultant velocity, and for a particular area of dA which is having a solid angle d sigma, uh, to do the integration over the whole area. So from there itself you can get an expression of the average velocity of C, that gives you 4 by 3 into C bar, that is the mean velocity. And after substituting it, you will get lambda as this. Okay, so this is the first order correction. And second order correction, which is much more refined. Okay, second order correction, that is basically demonstrated by Maxwell. Okay, second order correction, that is basically demonstrated by Maxwell. So in that case, what he have considered, so it has both the it has the elements from the first order also. So all molecules moves different direction, that is there, and also with different velocity. Okay, so previously the velocity all molecules are moving is fixed, that is c bar, but here Maxwell what has prescribed is much more realistic. So it also moves in different direction, and also different velocity. Okay, so the velocity is like varying from the velocity distribution curve, right? You know the velocity distribution, right, which is this, from this Maxwell velocity distribution. You know the velocity is like the kind of velocity that gas can have, right? So you here you have to do the integration of over the velocity also. Okay, over this distribution. If you do that, in that case, the lambda expression you will be giving as, you will be getting as 1 by root 2 n sigma. Okay. So in question, try to use this expression. Okay, because this is the more realistic expression of lambda. Okay. Uh, okay, this Maxwell one. Okay. If it's not specified, whatever expression you need to use, if it's not specified in the question, then try to use this second order correction expression, that is the Maxwell expression. Okay. So basically there are these three kinds of expression of mean free path is given. So first is this, lambda is basically c equal to c bar, so it gives 1 by c by sigma. These are the three expressions. Okay. Yeah. Uh, Now, if you know the C lambda, you can also calculate it from here, the value of tau also, right? So tau is basically uh, what is tau? Tau is c bar by lambda, right? Yeah, tau is lambda by c bar. Sorry, yeah. Tau is basically lambda by c bar. So from this, if you know, if you can calculate the lambda from itself, you can also calculate the tau also. So yeah, so this is a very important relation that you have to remember. This expression of the lambda. So in the question, maybe the gas density can be mentioned, gas means density and effective collision cross section. From there itself, you can easily calculate the lambda, the mean free path, and from there itself, you can also calculate this average collision time, tau. So this is very two important relations to remember. Okay, and yeah, and also the question can also come in a very different way, also in a very tricky way, you can say. So let's suppose in the question, instead of mentioning this gas density and let's suppose the P is mentioned, that means the pressure of the gas. Okay, so in that case, you can use PV equal to N kVt, right? So from here, so you can write N as in the expression of PV equal to, sorry, this is N kVt, right? So it should be N kVt. So if you move the V into the right hand side, it will gives you N by V into kVt. So gas, so the, what is this called, number density, we got density into kVt. Okay. Now from here, so N you can write as P into kVt. So if you plug it this N into the expression of lambda, which is 1 by root under 2 N sigma, you plug the N here, you can write lambda in terms of pressure also, right? kVt into root 2 P sigma. Okay. And for spherical gas, spherical monoatomic gas, sigma is basically pi d square, as d is basically radius of the gas molecule. So this is a very important relation also. Yeah. So these are very useful relations. Okay. So from pressure itself also you can calculate the lambda now. Now, using this kinetic theory also, you can basically from this mean free path, uh, you can basically calculate this pressure expression of the pressure also. Okay. Using this all this definition of mean free path, survivability equation, and all, you can basically calculate the expression of the pressure also. Okay. So it's a very useful thing to calculate, like to remember. Okay, so pressure from mean free path. This basically uses the kinetic theory of the gas. Okay, so it's basically, let's take you have a container of the gas. I just telling you like the how this derivation comes in a very uh, rudimentary way. Okay, so let's suppose this is the gas container. Okay, a small area element dA. Okay, so dA is there a small area element. So we want to see, let's suppose this is the dA element is there, a small volume element dV, which is at a particular solid angle at a distance r from this particular area dA, that is basically this area dA, and this particular volume, small volume element dV is having a solid angle d omega. Okay, so uh, from this, so this dV element contains some gas molecules n, right? So from this gas element n, uh, let's suppose the gas element the number of gas particles are n naught. Okay, so what will be the amount of n naught gas that can travel uh, that can travel uh, towards dA after the distance r. So that n naught, so that, let's suppose n is the number of molecules that basically travels from this this from this distance to this distance. Okay, so let's call it as A to B. Okay, so that is basically related by the survivability equation, right? So n is basically n naught equal into e to the power minus r by lambda. Okay, that we have already know. Okay, and n naught is expression can be written like this. This is a very Pc into n into dB into dt. Okay, dB into dt into d sigma by 4 pi. So where like Pc is basically the collision frequency. This is also at a particular time t. Okay, dV is the small volume element and d sigma is the solid angle. Okay. Now from here, now from this expression n equal to n naught by e to the power r lambda. Uh, so we got the number of molecules that survives from through this distance r. You got this expression. Now after that, so these gas molecules are basically what is this called? Since from kinetic theory, these gas molecules are basically elastic molecules, right? So it will, after suffering a collision, let's suppose it comes at angle theta with a velocity c. After the collision, since it's a elastic collision, it will also moves with a velocity c on the opposite direction. So during that, the total change in momentum we know is that delta p. Let's write it as capital P is 2 mc cos theta. Okay, and we know change in momentum is basically change in pressure into dt, right? So, and we know the change in pressure is basically df dt uh, into the change in area. Okay, so df dt is basically equal to dp. So if you know dp, we can, from there you can calculate the df, and if you know df, then from there you can calculate the delta p, that is the change in pressure. And if we, so this is for a single molecule, and here the total number of molecule is given by this n. This is a very big expression. So here you write all this thing Pc into n dB dt dA cos theta by 4 pi r squared into e to the power r lambda. So so since all of these molecules, these n numbers of molecules will be colliding with this area dA. So in that case, the df dt would be this whole big expression of 2n dA into 2 pi 4 pi into cos square, sorry, cos square theta sine theta d theta d phi dr c ds. Okay. Now if you integrate over this whole volume of the gas, in that case you have to integrate df dt. The integration limit would be on cos theta to be 0 to pi by 2 cos square theta sine theta d theta. On d phi it would be 0 to 2 pi, dr it would be 0 to c dt, and velocity can be anything between 0 to infinite. If you do the integration and all, after getting the expression of the force, the pressure would be simply df by dA. To put it there, you will getting the pressure expression as 1 by 3 ml c square bar. Okay. So this is the expression of the pressure from the kinetic theory of the gas. Okay. So as you can see, so if you know the mass, so this is a very this is the relation you need to remember. So uh, so the pressure is basically related to the mass of the gas, the number density of the gas, and the average the velocity. Okay, the square mean of the velocity of the gas. Okay. So if you know all these three things, you can calculate the pressure of an ideal gas inside a container. Okay. Okay. So yeah. Yes. So these are basically the important relation that we will be using during our calculation, like during solving all the numerical problems and all. So far what we have discussed, let me give you a summary. Okay, so basically we started from the gas, the mean free path of the gas. So the lambda expression of the lambda. So we first basically develop the integral form of the mean free path of gas. So since we know gas molecules collides when it moves in the atmosphere, so there its mean free path is given by this integral equation. Its average collision time is basically given by this expression, and from there so in order to get a closed form of these two expression, what we did, we first calculate the survival probability of the gas molecules. So from there we have calculated the x lambda, and from there we get the survival equation, which is a very important equation. Similarly, this is the survival equation when the gas molecule, let's suppose a certain number of gas molecules n naught is moving in space at a distance x. In that case, this is the survival equation. It is the n equal to n naught into to the power minus x by lambda. Lambda is the mean free path. Now let's suppose the same thing now with respect to the time. Let's suppose at t equal to t naught, t equal to 0 times, let's suppose n naught number of molecules are there. Now after a certain time elapsed t, what is the number of molecules remain? Okay. So in that case, the nt after the elapsed time nt is related to n naught by this relation, where n naught is equal to e to the power minus t by tau, where tau is the average collision time. Okay. And next is how, like, this is the expression of tau in terms of gas speed c and sigma. Okay. and tau, and this is the important relation between tau and lambda. Okay. Now what we discuss, so we need the speed of this tag molecule, okay, the molecule that we are interested in. So how to calculate the speed of this C? Uh, okay, so in order to do that, so what we did, so sigma we have before calculating the C, the expression of sigma, we simply consider the molecule as a monoatomic spherical molecule. The sigma is basically pi d square, that is the effective area of that particular molecule. That effective area is basically the effective cross section area of that particular molecule. Now during the to get the expression of C, what we did, we first considered that all the molecules are frozen. So in that case, C is simply C bar, that is the zeroth order. And the first order correction, we only considered that the molecules are moving with different direction but with same speed. And after doing the first order correction, this is the expression we got. And the second order correction, we added that apart from different speed, different direction, we also considered the molecules moves with different velocity also. And the velocity is ranging from this velocity distribution of the Maxwell curve. And after doing that, we got this expression of the lambda. This is the second order correction, which is the lambda is basically 1 by root 2 n sigma. So if you know the gas density and sigma, you can calculate the lambda, and from that itself you can also calculate the tau also. Next, we calculate the pressure using the concept of mean free path and kinetic theory. If the gas molecules are basically let's suppose the gas molecules are confined inside a container. So in that case, from the kinetic theory, what is basically the pressure of the gas? Okay, so that thing is basically we have calculated here. So this is the expression of the pressure of the gas molecule inside the container. So it's basically mn into c square bar. Okay, yeah. So now after so we have derived many things. So now we will be solving some of the problems. Okay. The first problem is calculate the fraction of gas molecules which have the mean free path in the range lambda to lambda. Okay. The options are basically option A is 0.14, option B is 0.51, option C is 0.37, and option D is 0.43. Okay. Uh, so we know from the, so here basically you have to use a survival equation, right? So after traveling a distance x, we know nx is n naught number of molecules. The survived molecules nx is basically n naught into to the power minus x by lambda. Okay, this is a survival equation we have derived. Survival equation. Okay. So now from the problem, it states that the fraction of molecules that which have the mean free path in the range lambda to d lambda. So that means in between this lambda to d lambda, the molecule will suffer some collision. So so let's suppose this is lambda and this is lambda plus d lambda. So between these two distance, let's suppose this is n1 number of molecules is there. Let's suppose it's initially there is n0 number of molecules. After traveling a distance lambda, number of molecules reduced to n1, and after from lambda travel to lambda plus d lambda, the number reduced to n2. Okay, right. So here it's not d lambda, it's 2 lambda, right? Lambda to 2 lambda, yeah. So n1 is basically n0 e to the power minus x lambda into lambda, and n2 is equal to n0 e to the power minus 2 lambda by lambda. Okay. So fraction means n1 by n0 into to the power minus 1 n1 by n2 into to the power minus 2. So the number of molecules that have this much amount of mean free path should be n1 minus n2, right? And the fraction would be n1 by n0 minus n2 by n0. That would be e to the power minus 1 minus e to the power minus 2. That would be 0.37 minus 0.14. So that would be 0.23. Okay. So the answer would be 0.23. Now the question 2. Calculate collision frequency of oxygen molecules at STP. So given some information are given. So given is number of molecules per cubic meter is 3 into 10 to the power 25. Diameter of oxygen molecule is, so they are basically approximating the oxygen molecule as a spherical kind of a particle. Okay, so that's why they are mentioning the diameter of the
They are
oxygen
considering it as hard sphere.
heart sphere. Yeah, that's why in the question they mentioned this as a diameter, the diameter. So yeah, now so these are the given information. Now the options are: option A is 8.3 into 10 to the power 9. Second inverse. Option B is 8.2 into 10 to the power minus 11. Second inverse. Option C is 7.3 into 10 to the power 9. Second inverse. And option D is 6.2 into 10 to the power 10. Second inverse. Now, since so we know this, so collision frequency you have to calculate. Okay, that is nothing but the lambda thing. Okay, that is actually known as also collision frequency also. Okay. Oh, sorry, not lambda, the tau thing. Okay. Yeah. That I guess tau or 1 by tau. 1 second.
Tau was time period, so 1 by tau, I
Yeah,
think.
1 by tau, yeah. So 1 by tau is the collision frequency, okay. Yes. So that means it would be, yeah, it would be c by lambda, yeah. So here you can c bar by lambda, okay. That is one, sorry, that is the collision frequency. You can write it as f, okay, 1 by tau. Okay. So yeah, so lambda, you can calculate the lambda as, so lambda expression, there are several expression of lambda we have discussed, right? That first order, second, zeroth order, first order, second order. So since in the problem it's not mentioned, so it's better to order the second order correction. That is this expression, okay. This one lambda. So lambda would be 1 by 2 n sigma. So that means, so root 2 n pi d square. So now here n is the density, right? So density of the gas is mentioned. That is this 3 into 10 to the power 5, right? 3 into 10 to the power 5, 25. Sorry, 10 to the power 25. Number gas number density and area you can easily calculate. So from that you can easily calculate the this lambda thing. Okay, now after if you calculate it, will give some this kind of value, 5.8 into 10 to the power minus 8 newton. So be careful about the units, okay. So here everything is in SI units, so meter and watt, try to use. Now from here, so F is given by c bar by lambda, okay. So c bar is basically what is 8 pi by kbt, right? Yes.
The in the lambda formula it's 1 by root 2 and n sigma, right? Like the n and sigma are not under the root.
Oh, sorry. It's root 2 is there. Yeah,
Yes.
yes. Same.
Yes, yes.
Sorry. It should be root 2. Yeah, root 2. Yes, in the expression also you have written correctly. Yeah, this is the correct one, n sigma. Yes. So it would be uh, yeah. So anyway, so uh, into lambda. So it would be 8 by pi into kb value 1.38 into 10 to the power minus 23 into, since it's mentioned in STP, so the temperature is 273 Kelvin, right? In room temperature basically STP means, by this mass is also mentioned, which is 5.31 into 10 to the power minus, mass is not mentioned, right? So yeah, mass of the oxygen molecule is, you should, like, the question it says should mention, okay. Anyway, uh, it's actually required. So it's 5.31 into 10 to the power minus 26 is the mass of the oxygen molecule, by lambda 5.8 into 10 to the power minus 8. So now if you calculate this frequency, it gives you 7.3 into 10 to the power 9 second. So So this is the collision frequency. So main thing is the how you calculate this, the procedure to calculate. Okay. So collision frequency is just 1 by tau, that is c bar by lambda. So two things you need to know. One is c bar, next is the lambda. So lambda, you know the from the Maxwell law. This is the formula to calculate the lambda. So you know the gas density and all, diameter of the oxygen molecules. And next is c bar. C bar you know from the our Maxwell distribution. So everything and temperature and all these things are mentioned since it's in STP. So from there itself it easy can easily calculate the collision frequency like for this kind of problem.
How did you take the mass?
Mass is actually although it's not mentioned in the problem, but in actual problem it should mention. Okay, in this problem it is not mentioned. Okay, so I just search it from the Google, so it's given this like the mass in kg. Okay,
Oh, okay.
yeah. I mean, in the actual problem, I hope it's mentioned. Okay.
Okay.
Okay. So next problem is yeah, a beam of molecules is passed through a low pressure gas. Okay. The mean free path of the molecules in the gas is basically given by 5 into 10 to the power minus 4 meters. Okay. So the mean free path of the gas molecule is given. So gas molecules is passing by a passing through a beam of molecules basically pass through a low pressure gas. So that means it will face collision. So there should be a mean free path associated with the gas molecules to the beam of the molecules, right? So that mean free path is 5 into 10 to the power minus 4 meters. So find the fraction of molecules that do not undergo uh, collision while traversing the thickness traversing the thickness 5 into 10 to the power minus 5 meter through the gas. Okay. So the options are option A 0.1, option B 0.90, option C 0.99, and option D is 0.5. Okay. Yeah. So the thing is like a certain number of gas molecule is moving through a particular thickness. This suppose this is a number of gas molecules. Initially it was N naught. Is moved through a particular thickness of 5 into 10 to the power minus 5 meter. Okay, delta x. So the now some of the molecule will face collision, right? So some of the molecule will be from that particular beam. Some of the molecules will be will not come to the other side of this certain area, right? Because some of the molecules will suffer collision and they will be comes out from this beam, right? So let's suppose that number is survived number is n. Survived number of gas molecules are n. And here the mean free path is lambda is basically 5 into 10 to the power minus 4 meter. Okay. The mean free path between two collisions. Okay, so it's easy, right? So we know the survival equation. N is basically n naught into 10 to the power minus x by lambda. So here, just put the numbers into the expression. So n is basically n naught. So you need to calculate the fraction. So that means n by n naught you have to calculate. N by n naught is basically e to the power minus x is 5 into 10 to the power minus 5 by 5 into 10 to the power minus 4. Units are correct. So to the power minus 10 to the power minus 1. Okay, so if you calculate this into the calculator, it will give around 0.9. Okay, n by n. Okay. So although it looks a very difficult problem, but it's not that much difficult. It's a very easy problem. Just you have to use a survival equation. Okay. Question 4. The beam of molecules is passed through a low pressure gas. Sorry. Writing the same question. Yeah, the mean free path of molecules of a certain gas at pressure P and temperature T is 2 into 10 to the power minus 5 centimeters. So the mean free path of the particular molecules of a certain gas is mentioned. So it's asked you to deduce the mean free path at pressure P by 2. So they basically reduce the pressure of the gas molecule by half an amount, and temperature to T. So initially the gas molecules are having having pressure P and T, have a certain free path that is 2 into 10 to the power 5 centimeter. Now if you increase the pressure, if you decrease the pressure by E by 2 and increase the temperature by twice, in that case what would be the change in the mean free path? Okay, that you have to calculate. Then the options are option A 5 into 10 to the power minus 6 centimeter, option B 1 into 10 to the power minus 5 centimeter, option C is 8 into 10 to the power minus 5 centimeter, and option D is 2 into 10 to the power minus 6 centimeter. Okay. So to do that, what you have to do basically, so yeah, so we previously have derived the lambda, right? So in terms of the pressure, right? So this is the expression of the mean free path lambda in terms of the pressure, right? So in this case also we will use this same expression, right? So we know lambda is basically 1 kt kbt by unit under sigma into p. Now, so lambda basically is proportional to T and pressure P, right? That is the important thing. So if you do the take the ratio of two, let's suppose two mean free path, lambda 1 and lambda 2. In that case, it would be T1 by T2 and P2 by P1. So it's inversely related to pressure and directly related to the temperature, proportionally related to the temperature. Okay. So now, so the lambda 2 would be in that case, that means lambda 2 is basically equal to uh, T1 by T2, yeah. So lambda 2 would be T2 by T1 into P1 by P2 into lambda 1, right? So T2 is basically 2T by T into, so say suppose T1 has temperature T initial case and P1 has pressure P, and after the change in temperature T2 let's take 2T and P2 let's take T by T. Okay, so 2T by T and P by 2, so it becomes uh, so T cancel, so it becomes 4 into, yeah, 2 to the power 10, 2 into 10 to the power 5, 2 into 10 to the power minus 5, so it would become 8 into 10 to the power minus 5 centimeter. Okay. So the answer would be this one. So similar, just you have to use the expression in terms of the pressure. Okay. So 7, question number 7 is, sorry, question number 7 is 5. Question number 5 is for group of molecules traveling in a free space, what percentage of molecules travel a distance greater than 5 lambda. Okay. But lambda is mean frequency, so lambda is mean frequency. Okay, so the options are A 0.67%, option B is 67%, option C is 23%, and option D is 13.5%. Okay, it's easy, just uh, so we know if n is number of molecules initially, after a certain amount of time, if nx is the, after traveling a certain distance, nx is the n is the number of molecule. In that case, nx is n naught into certain probability of that probability denoted as fx, right? Fx is basically the probability of the molecules that doesn't suffer collision, and that fx probability we have basically written like e to the power minus x by lambda. Okay. So if you calculate this probability fx and multiply with it 100, so this gives you basically the percentage of molecule that doesn't, that basically have the mean free path greater than 5 lambda. So that means those numbers of molecules survive this distance 5 lambda. Okay. So fx is basically, that means here will be e to the power minus 5 lambda by lambda. So e to the power minus 5, to calculate e to the power minus 5, it will gives you 0.0067. Okay. If you multiply it with 100, so this gives a probability, the percentage as 0.67%. Okay, so this is the answer, 0.67%. Yeah. So, so the next problem is problem number 5, problem number 6. Mean free path of nitrogen molecule at STP is given by 6.85 into 10 to the power minus 8 meters. So in that case, calculate collision section of the molecules. Okay. The options are option A. Option A is 1.46 into 10 to the power minus 20 meter square. Option B is 38.37 into 10 to the power minus 20 meter square. Option C is 62.89 into 10 to the power minus 20 meter square. And option D is 19.76 into 10 to the power minus 20 meter square. Okay, so now, so the lambda we know. So since it's the question, it's mentioned in STP, right? So STP means we know the pressure and all. Okay. So for STP, we know the pressure is like 1 atm, right? So 1 atm. If we write it in bar, so it will looks like this, right? So pressure in atm, 1 atm is basically 1.013 into 10 to the power 5 bar, I guess, in SI unit. Okay. So in STP, let me just check once, 1 second.
We have to convert in Pascal, right? It's
Yeah.
SI, that's why.
So I forgot the unit. So it was Pascal per meter square, something like that.
No, no, it's Pascal only, Newton per meter square, which is
Newton per meter
abbreviated
square.
to
Yeah,
Pascal.
it's Newton per meter square.
Yes.
So it will be Newton per meter square. Force per unit area. Yeah. So now it's fine. Yes. Now it's fine. So okay. So now lambda is 6.85 into 10 to the power minus 8 meter. So using the similar expression, so we know in terms of pressure, so the expression looks like that. So basically lambda is kBt into root under 2 sigma into pressure. Yeah. Hmm. So now from here sigma is basically kBt into root under 2 into p into lambda. So kBt we know 1.38 in 10 to the power minus 23 into 273. That is the temperature in Kelvin, and root under 2 into 1.013 into 10 to the power 5 into 6.85 into 10 to the power minus 8. So sigma would be, if you calculate this whole thing, so it will gives you some value like 38.37 into 10 to the power minus 20 meters square root. So this is basically the answers. Okay, so main thing is like here, like you have to calculate the collision cross section. So pressure, temperature. So whenever in the problem it's mentioned the STP, everything, the pressure, temperature, and all. The lambda is already mentioned, so you can easily calculate the collision cross section. Okay. Next, is the question 7, question 8. The mean free path of the molecules of a gas at 25 degrees centigrade is 2.63 into 10 to the power minus 5 meter. Okay, this is the mean free path of a gas. If the radius of the molecule is 2.56 into 10 to the power minus 10 meter, then find the pressure of the gas. Okay. So we have to use this other formula. So this formula, the previously written formula. So okay, you cannot use a kinetic theory here since the mean free path and the radius is given. So we can calculate the cross section area, and we know the lambda. So from there itself we can calculate the pressure. So yeah, so options are option A, 153 Pascal. Option B is one. So option B is 168 Pascal. Option C is 135 Pascal, and option D is 210 Pascal. Okay. So these are the options are given. So now the thing is, this is the question number 7. So okay. So to solve this the similar way, so we know P equal to NKT, where is N equal to N by V, and we know this expression of this lambda. So lambda is basically KT by root 2 sigma by P. So from here P can be written as KT by root 2 sigma by lambda. So sigma is, we know, pi by d square. So from here the radius is given, so you can calculate the sigma. Just put it here. After doing that, kbt, you know, 1.3 into 10 to the 10 to the minus 23. Temperature is 25 degrees centigrade, right? So it should be T should be 273 plus 25, so it would be 298, right? 298 Kelvin. So T is 298 Kelvin. So into 298 Kelvin. Root 2 is there, sigma is there, lambda is what is the lambda? 2.57 into 10 to the minus 10. No, sorry, 2.60 into 10 to the power minus 5. 2.63 into 10 to the power minus 5 Newton. Now, if you calculate all of this, you will be getting 135 Newton per meter square. That is 135 Pascal. Okay. So 130. So as you can see, there are multiple questions can come from a single formula. Okay. So like either you can be either in the question it can be mentioned lambda. From there you can lambda and pressure can be mentioned. So from there itself you can calculate the collision cross section. Or in the problem it can mention the lambda and the collision frequency and all. From there itself you can calculate the pressure. Okay, so this formula is a very useful formula to remember, right? Many types of problem can arise from this formula. Okay. Next problem is similar type of another problem. Okay. So the question 9. So this question 7. So it's a question 8. Question 8. Similar kind of question. If the mean diameter of ear be 3 into 10 to the power minus 10 meter, to what pressure must a vessel be evacuated if its mean free path is to exceed 10 centimeters. So very high mean free path. Okay. T is 273 Kelvin. Okay. The options are option A 0.024 Pascal, option B 0.133 Pascal, option C 0.094 Pascal, option D 0.104. So the question is like, so let's suppose okay. So the in the air, so air molecules are there. So the air molecules mean diameter is mentioned. So in the question itself, it's mentioned that what should be the pressure of that vessel where like the air molecules are. So what pressure we should exert into the vessel in order to make the mean free path among the gas molecules to exceed 10 centimeter. Okay, so for that, I mean to get this I mean this kind of a mean free path scale, we need to reduce the pressure of that vessel, right? uh, so that mean kinetic the movement of the gas molecule will be become slower. So in that case there would be less probability of collision, and the mean free path will be exceed, like the mean free path will increase, right? So for that reason you can see the options, in the options of the values of the pressures are very low. Okay, so similar way the procedure is similar. Okay, uh, the lambda is, lambda is kBT by root under 2 P into sigma into uh, P into sigma, yeah. And for P is in kBT, P is the pressure, the ideal gas. We are considering the gas to be ideal. Temperature is mentioned is 270. So T is 273 Kelvin, and pressure is the expression of pressure in terms of lambda and all. It would be root 2 lambda. So P would be this side, so root 2 lambda sigma. So it's now you can easily calculate the same way, 1.38 into 10 to the power minus 23. Temperature is 273. Root 2 we know. Lambda is mentioned is 10 centimeter. It needs to have 10 centimeter. Right? 10 centimeter. It's converted into meter. Okay, because everything is a unit. So 0.1 meter into the collision cross section. Okay, so if you calculate this thing, the pressure would be 0.094 Pascal. So as you can see, very less pressure it needs to have to achieve such kind of a such kind of a high mean free path. Okay, yeah. So next problem is next problem is a very easy problem. Okay, so 9 problem 9 in an assembly of 1000 molecules each moving with same same velocity, calculate the ratio of the number that would travel undeflected even after traversing a distance equal to 0.5 lambda to 1 lambda. Okay. The answers are option A is 1.65, option B is 2.84, option C is 3.79, and option D is 0.58. Okay, these are the four options that are given in the problem. So 1000 molecules that moves with the same velocity. So calculate the ratio of the number. Ratio, you know, the ratio means like the fraction here. So to calculate the fraction of the molecules. So the same way, okay. So we know that N is basically N naught into e to the power minus x by lambda. Okay, it is N1, so its N2 is N naught is x1 e to the power minus x2 by lambda. Okay, so x1 is basically here 0.5 lambda. So here it's a mention, it's a mention that the number of molecules that would undeflected, the ratio of the number of molecules. So the undeflected case for the case of 0.5 lambda is N1, and the undeflected number of molecules for the case of 1 lambda is, let's take N2. So here x2 is just lambda. So N1 by, sorry, so N1 by N2 is simply to the power minus 0.5 lambda by lambda by e to the power minus 1 lambda by lambda. So it will be power minus 0.5 into e to the power minus 1. So if you calculate this will give you around approximately 1.65. So basically, so that means the ratio of molecules is like 1.65. That don't have like any relation. So the correct answer will be option A. Okay. So okay, so with this, so this is the last problem we have solved for this session. If you have any question, you can ask. Otherwise, I will close the session. Okay.
Thank you, sir, for the session. I just have one request that can you please share this PPT in the group?
Okay, I will share it into the in a folder, Google Drive folder. Then I will share the link with you guys. Okay.
Okay, okay. Thank you
Okay.
so much.
Okay.